For today, we're flattered to introduce Mr. Adil Gürkan Ceyhan to insight us about the drilling geomechanics. Mr. Adil Gürkan Ceyhan is a geoscientist and geomechanics advisor to TEPO since May 2020. Formerly, regional drilling and measurement reservoir domain based in Al Khobar, Saudi Arabia, in the years between 2015 to 2020. He has a 23 years experience with Schlumberger information testing and sampling, production logging, and various cased hole and open hole measurements to address well and near well bore problems. He started his career as wireline field support engineer and worked in the field for more than a year, then joined the interpretation development group and worked in various assignments in Oman, Dubai, Kuwait, Angola, Guinea, Islamic Republic of Iran, and the North Sea, mainly in formation testing and sampling. Mr. Ceyhan, while based in Stavanger, Norway, where he was involved with a drilling group to support formation pressure and sampling while drilling operation design, exclusive, and fleet testing. Ceyhan later qualified with the most complex drilling tool, formation sampling while drilling Spectrosphere for Saudi Aramco, where he also involved in horizontal wellbore stability prediction and modeling for tight sandstones and carbonate fields. Mr. Ceyhan has a Bachelor of Science and Master of Science degree in Petroleum Engineering from both Istanbul Technical University, Turkey. So without any further ado, Mr. Adil, the stage is yours. And if any of our participants has questions, they may ask them in the chat side, and I will later on forward them to Mr. Adil Gorhan Ceyhan.
Thank you. Thank you very much for this nice introduction. So today we'll talk about drilling geomechanics, but particularly also, we will focus on wellbore stability for the onshore and offshore wells, and also we will touch on the how we do the propulsion and frac gradient prediction for the wildcat and exploration wells in mainly offshore environment. So basically, drilling geomechanics, it's you're riding a bicycle and then you are turning the headlight on, right? But it doesn't mean that you have the headlight on that within a 50 meter, even though you have the lights, you have a rabbit is gonna cross or maybe a wild pig is gonna cross, right? Of course, those unexpected features, right? If you go slow or if you go bit more precautious, right, you have an advantage, right? So just keep in mind that you are riding a bicycle and we are on the midnight and then we are putting the headlight on, but still you have to ride the bicycle yourself and then still expect the unexpected while going through this route. So geomechanics, what is geomechanics, right? So we know that the mechanics, geo is the rock and the formation, and the physics of the formation, right? Simply. So where does geomechanics has an impact, right? So I'm sure several of you have been involved in the drilling operation and the completion or the production. You will eventually hear that issues having on the casing settings, overpressured zones, the fault stability problems. And of course, when you go for a fractured zone on a horizontal well, lost circulations, right, and unstable zones, and of course, potential stuck pipes. And eventually, if you want to complete, do a stimulation, you need to know the fracture tendency of the formation. And furthermore, of course, when you try to deal with the longer duration of the reservoir, you eventually get into the potential subsidence, compaction, and other issues related to the geomechanics, right? Simply, geomechanics actually applies, from well to field, from appraisal to abandonment, right? So actually, there is when we talk about geomechanics and with the predictions, right? It's a very good analogy that we can make with the horse racing, right? Horse race predictions. Actually, there was a good catch, when you try to explain this to like in Saudi Arabia or Kuwait or people have an education in the UK, they really go with the horse race and they understand the horse racing principles, right? So when you try to predict the horse race winners, right? This case, let's say we go back in the future because I was, I grew up, on 2 years when I first come to Istanbul. I was very close to, Veli Efendi Hippodrome, right? So and I was actually spending my weekends, right, going watching people, right? It's a nice, of course, if you watch the Gazi Koşusu, right, it will be something really spectacular, right? So of course, when you look at those papers, right, the prediction papers, they talk about the horses, right? Even the mother of the horse, father of the horse, right? So when you talk about the basketball or football, no one talks about the mother of Ronaldo or father of Ronaldo. But when you talk about horse racing, it's really important, right? So the disease, muscles, weight, heights, right? So those are the horse properties, of course, right? And there are other factors like outside factors, right? So is this gonna be taking place in Bursa or in the or in the grass or on wet grass, right? Or rider will be Halis Karataş or will be another rider. Those are all important when you want to do horse race prediction. In a sense, what we do with the mechanical work model, it's very similar. First, we have to do the mechanical properties of a given well location, and of course, we have outside factors such as like pore pressure and downhole stresses like vertical stress and minimum and maximum horizontal stress, right? So with that, once you have that complete mechanical earth model, so this can be 1D, of course. Eventually, we want to reach that 3D model, right? You can define the frac design, and you can maybe give a guidance for the drillers, and of course, you can maybe define a gravel pack operation, and you also give a heads up for the potential losses locations before drilling commence, right? So when you put together, right, so there are several things that needs to be considered for the mechanical work model. Firstly, we have the critical input data such as Varlan logs, and of course the seismic cubes, and must have also the core data, and as well as drilling information, right? So when we talk about the Varlan logs, is critical one is the acoustic, the sonic logs, and density and porosity logs is the critical inputs, right? And of course, when you want to define mechanical properties, you have to define the Young modulus, Poisson ratio, friction angles, and so other parameters. So I will come to those details in coming slides. And of course, you need to calibrate, you need to model also the vertical stress. And there is a way, of course, you can also model the SH min, the horizontal minimum stress, but there is no direct way to measure SH max, which is the horizontal maximum stress. But you can infer from the further history match of the caliper data, which today's software is capable of that. That you do the history match and to understand the SH max. Also, the direction of the SH max really critical from the image data and the caliper information. Then, of course, you can design wellbore stability with this information. You can do the standing analysis, frac design, compaction, subsidence, and reservoir simulation. If you do coupled studies, this will be the critical input, right, for those studies. So actually, when we do talk about 1D, a simple 1D, let's say you talk about 1D mechanical model, first you start with the data audit, right? Then this data audit goes through a framework model, understand the geology, and of course the potential drilling hazards if you have the offset well studies, and then you try to start creating the mechanical stratigraphy based on this, and then from the offset well density logs, you also create the overburden stress. That's the first primary stress that we need to really get it right first. If you don't get the overburden right, so you have all complications. So that's why every step has own its critical weights, but overburden stress is the must-have, needs to be correct at the beginning. Then of course the pore pressure. Today we have capable of measuring pore pressure in the drilled well. Also while drilling we can take formation pressure tests as well. And also if you have some flows happen during drilling, of course it gives you well control issues. It gives you also the pore pressure information, and of course nearby well production also gives you an idea about the pore pressures. Then you come up to the rock strength and elastic properties. So then you involve with the of course the uniaxial compressive strength and of course bit of a the core study, triaxial core studies, and of course the velocity input, velocity inversions. Then you model your yaw strength and elastic properties. Then again, horizontal stress direction. The as I mentioned earlier, oriented calipers in images and the acoustic data will give you a help on understanding stress azimuth if there is any preference for the maximum stress direction. Then again, minimum stress calibration. We are today mainly utilizing the lick-off test while drilling, right, to understand. And every casing shoe, we have the we have the lick-off environment and understand the lick-off trends and establish the minimum frag trends. And of course, we can do as well include the mud loss and mini frag test approaches, and of course with the dual pecker while on operation, you can also do the mini frag test and also calibrate your minimum horizontal stress. As I mentioned, also we cannot measure directly the maximum stress, but you can model it with the history match of caliper data, and of course what's critical input, also the images and azimuthal caliper information. Then of course you go and back and do the more Coulomb type failure analysis. Like this can be also the again the cavings, mud losses, and of course if you have some sending information coming from the nearby wells, you can also have an understanding that to model that failure prediction for the environment. So as a small cartoon, actually it's from the one from 1D mechanical model generated. So here basically we are going for a carbonate sequence. Then we have the sand, and then start the shale and sand, and of course from the left we have the pore pressure, and then the red here is basically our breakout trends or the more Coulomb failure trends, which means that the mud weight you need to support this, and the mud weight needs to be heavier than this. Then you can minimize the washouts and the changing in the wellbore conditions, right? And of course, what you limit yourself is the leak-off trends, which is the light blue here, and of course there were some leak-off test has been done, and then we know that also you calibrate the leak-off trends for the leak-off test. Here is the diamond shape here over here. Then of course we have the breakdown trend, which is the overburden as vertical overburden gradient here. So everything here is given as is in PCF. I will explain what this PCF means in a bit. You get a better understanding. This is actually the mud weight. We are when you plan, especially in the onshore Turkey, we are generally using the PCF. Then of course we have the breakdown trend, of course, in the similar. So here the white area, it's our basically the drilling envelope we call, right, or the mud weight window. So we're gonna refer this always on the coming slides. Keep referring this the window. Then of course what we use is the caliper and tight spots, from the drilling observation and the caliper change. And of course today software is capable of predicting the failure. So basically you do a forward model to match this failure to understand that how is your SH max calibrate with the 1D mechanical inputs. So, and every aspect, of course, we have, we talk about wellbore stability. There are things that sometimes you cannot control, or you can control if you plan in advance, like the rig type and drill pipe casings, trajectory, like bottom hole assemblies, and of course the drilling fluids, right? Those are also the critical parts. So to have such a washed out or badly washed out wellbore. So if you look at the root cause, there could be several of them, and could be maybe mixed of, right? So today, basically, we're gonna focus on, of course, the overbalance and the type of lithology, and of course the ECD, but other things like selecting the bits, ROPs, then other type of drilling activities has a critical impact on drilling geomechanics, right? So that's why, I mean, once you have this external factors which you cannot control directly, those could be, on the left side, I just put it here. So what you need, then you have the certain mindset, and then some calculations and certain practices, right, needs to involve in this type of analysis, right? To not only just the modeling with the softwares, so you also need to do how you're going to apply these practices, and also see how you're going to collaborate with the field people, and how you're going to collaborate with also similarly with the asset team, the same time. So in a sense, the geomechanics engineers or geomechanics team, it's like the interface between the drilling and subsurface, right? So you make that interface. So when you talk about drilling and the measurement, of course, for a drillers, drilling is always big, and the measurement is it's small, right? So then, not I mean, when you talk to the drillers, they always hate to have that some measurements done in their wellbore. But of course, for them, it's shoe to shoe. They have certain KPI. Shoe to shoe means that you have casing shoe to casing shoe. There are certain KPIs to reach that target, and once it's done, right? So basically, drilling stands for means it's done. But when you talk about measurement, right, it's it can be maybe, right? So always you talk about maybe. So this brings that as maybe question always when you do the analysis, right? And of course, the question always you should ask yourself. So okay, they have the KPI on shoe to shoe time targets, but how you define the KPI for measurements, right? This is always something that you need to think about. Right now, I mean, okay, we reached a certain level that then we need to understand the pore pressure a little bit. Then we go to the wellbore stability. It's a bit rather crowded slide, but I'm not going to focus on the left side here. But basically, what we do, on the current, especially if you have a wildcat, you have the seismic interpreted, and then you receive the 1D model. 1D model for the velocity, and from that velocity you need to invert on and of course to understanding the bit of the geology in the region, try to create before drilling, try to create with inversion, estimate the pore pressure, right? So I will talk about this how it's been done, especially if you are going through planning a wildcat well and also if you don't have much of an offset understanding. So let's talk about this, how we do the pore pressure modeling. So before going to that, I just mentioned earlier that there are certain useful conversion that their water density. We know that seawater is about 1.03 gram cc, but when you convert on ppg, this is like it becomes 8.65, right? And if you talk about 10,000 feet of normal, like say, then we take that gradient of 0.44 psi foot. But then of course when you convert this to ppg, let's say if you have 1.5 mud weight, so then this is becomes 13 ppg. Then vice versa, you can convert that gram cc to ppg or pcf, right? So as I mentioned earlier. And also an overboarding gradient. There are, of course, rule of thumbs. On a deep water, we have, we see there 0.8 psi foot. But for the land, when you go to the, Karakush or onshore Turkey, you can go up to 1.2, 1.3 psi foot. So those are the good rule of thumbs of, overburden gradient. And of course, you can convert the equivalent mud weight always to pressure, which is simply you have the TVD, and then there's a multiplication factor is 0.052, basically, as you can take simply. So as I mentioned, the drillers, they would like to talk about always the with the equivalent mud weight. So when they refer anything in the well, so that's why since you are producing something on pressure, you always need to convert this into the equivalent mud weight, which is either ppg or pcf. Okay, so basically downhole environment, right? So let's say we have the two communicating points that we have normally pressure gradient, right? So of course here we have the gamma ray basically is identifying that normal pressure hydrostatic trend, right? Then those are easily you can see that the factor it's applying the similar normally pressure trend, which is very close to hydrostatic, right? And of course, if you have additional perfect seal in between, like a shale, because of permeability, it isolates, but it creates that a shift in it follows the overburden trend. But in between, we have the sand layer still has a good communication through up and down, which creates the abnormal pressure, right? So simply, this is how the downhole pressure environment develops when the deposits happens over the geological time. But when we go back to in the past that Terzaghi first really understood this. Terzaghi is an interesting character because he spent some time in Istanbul during the First World War as part of the deal with the Hungarian Austrian Empire, with the Ottoman Empire. Then also he teach people in Istanbul Technical University and as well as Bosphorus University that time. But then he did some studies that he understood that rock matrix does not support the full load of overburden and horizontal stress. It's calibrates with itself is the effective stress, right? So basically, you have the overburden gradient, but then the rock itself only feels that the effective stress, which is overburden minus the pore pressure, right? So any pore pressure methods that's been developed afterwards, like Eaton, Bowers, right? It's basically simply try to find that effective stress term. And of course, once you know your overburden gradient, you can simply do the minus, and then you can obtain the pore pressure trends, right? Again, the first step is you need to get the overburden gradient, right? So this is very important. We call S vertical sometimes overburden gradient. Then of course this is you can do with the density logs with some of course some seismic as well. You can do some correlations available, and then you can estimate based on this with the given locations with the change on velocity. You can see if the trend is changing, especially on a logarithmic scale, the slowness, which is the we call DTCO, okay, sonic slowness. You can calibrate this and estimate the changes in effective stress, and then simply you are basically start assuming that your pore pressure. So basically, if you have a normal compaction trends, right, then you know that porosity starts, let's say, with the surface up to 50%. When with the normal compaction trend, the porosity decreases, right? So normally, if you have a single compaction line, it's usually your life is easy. You can make easy correlations. But if the multiple compaction lines comes into play, and of course, pore pressure modeling becomes rather complicated, right? And sometimes really difficult, right? That's why you need some additional measurements, especially if you are dealing a wildcat in offshore. So let's go back and again check that based on porosity change, overpressure related to the porosity, we have normal pressure with the normal trend line. Of course, we have the faster deposition, and pressure doesn't have enough time to equilibrate with the above and below. Of course, that porosity stays and creates an overpressure region, right? And if you look at the other logs, like this can be porosity log if you are measuring, or as I mentioned earlier, slowness with the delta T, or resistivity logs. You can also do that, effects. Of course, you need to also understand that you are only applying this across the shale, because the trend application on the sand, if you are going through the sand, it doesn't really work. So make sure you really understand that trend change over the shale intervals. And also, what they do, drillers, of course, they have this, the exponent values. They utilize the ROP, RPM, and weight on bit and bit size. And of course, Change in trend, it gives you the anomaly that you are potentially maybe going through a pressure ramp, right? But again, this is developed for the roller cone bits. It doesn't really apply the diamond bits that you are using now commonly in almost all the environment. But this is an option again. Try to utilize with the drilling parameters, right? Uh, Simply we have the porosity methods, the sonic methods, resistivity, density, and then mentioned the exponent. But most effective one, because becoming that sonic delta T, which you can easily correlate that and rather not effective with the lithology. You can see the sonic trends and do that pressure estimates based on sonic data. So today also we are utilizing this mainly in offshore with the real-time LWD information. So when it comes to that, vertical stress, as I earlier mentioned, it's very critical. Okay, you have the let's say you are in offshore, you have a certain density log measured on a certain interval, but then from the mud line, we call the bottom of the sea, up to the sea level, you need to assume something, right? So normally there are correlation, you do extrapolation, but of course, this gives you maybe, of course, question marks that if there is a heterogeneous environment during that, in that interval from the overburden interval, it's complicates that S vertical calculation. But if you don't have anything else, you need to do this extrapolation and use this as a overburden gradient for your calculations. And for modeling horizontal stress, we have empirical correlation has been developed mainly for the Gulf of Mexico. That now is been used, and also published in so many different books and papers. Then, of course, they relate to the effective SH mean and effective S vertical with the K factor. Then that empirical methods, that K factor has been also slightly modified over the years, right? And lately, Ethan also find the relation with the Poisson ratio, which I will explain what the Poisson ratio means in a bit. And of course, back calculate from the Likov tests. And simply we have the Hooke's law again. This is a bit of on a later applications, but today with the softwares are capable of utilizing the tectonic system parameters, which is the epsilon parameters. That's what we are utilizing to understand that SH min, SH max when you calibrate with that caliper and other informations with also Likov test. Of course, here is the we need to define Poisson ratio and Young modulus. What are those? Simply, those are the elastic properties, right? I'm sure you heard about this, several times. But what are these? Poisson ratio basically is the measure of lateral expansion versus the longitudinal contraction. Very good example, actually, it's the cork, a bottle cork, right? So guess what? I mean, of course, you are using you're opening that bottle. You are applying the pressure from both sides, but there you don't see longitudinal, contraction. Then of course, then you can refer that the cork has a Poisson ratio is almost zero, right? So this is a dimensionless parameter. It can be from 0.1 to 0.5 for the rocks. But the cork is one of the good examples, right? Young modulus is the ratio of applied stress and the resultant strain in the same direction. It can be thought of as the stiffness of the rock. Of course, Young modulus we can calculate from the logs. We can also measure in the lab, which I will come in a bit. But once you calculate from the logs, you get the dynamic parameters, and you have to convert this to static. That's why when I refer Young modulus, STA means Young modulus static, Poisson ratio static. Those goes into that your calculations to understanding the stress. Let's look at some examples, the pore pressure and the fracture gradient cases. And one of the things that, of course, we are mainly dealing with the primary under compaction and the simple tectonics, but you also need to think about that there are secondary trap mechanism, on clay diagenesis, in hydrocarbon maturation, and the charging from several sites. also laterals, up-dip reservoir pressure, lateral transfer creates the secondary mechanism. To understand those are not that easy, of course, with the simple 1D or simple 1D velocity models. But still, with the primary, under compaction, disequilibrium, and you can understand from that 1D models and 1D approaches, right? Just to add that, when you have the hydrostatic pressure during compaction disequilibrium, you have the normal hydrostatic pressure gradient during the with the relation with the vertical depth TVD. If you have a low permeability barrier, as I mentioned a bit earlier, then with the compaction, speed exceeds that pressure equilibrium and doesn't equilibrate above and below, and then you end up having some high pressure trend below that impermeable barrier. So in this, actually, it creates the importance of clays. So clays bearing the sediment make up roughly 80% of the geological column. I mean, today, if you look at the Black Sea, the majority part of that, it's really filled with the clays. To understanding the clays in terms of seal or maybe source rock, and also the compaction trends, diagenesis, serve as the creating one of the critical abnormal the understanding of the abnormal pore pressure input. Again, clay properties, clay modeling across that region, it's very critical to understand that how the basin behaves with the pore pressure. Moving that, again, relative stress magnitudes, we have three types of faulting. So as you all know, especially if you have a geology background, we have normal faulting, strike slip, and truss faulting. So when you talk about North Anatolian fault, or Anadolu in general, or talk about Adıyaman, Batman region, and in a sense maybe a portion of the Akdeniz basin, you have that very faulted area, and then really strike slip tendency controls the trends. But when you come to the Black Sea, you are far away from all the tectonic activities. Then you really on a normal faulting, which is the S vertical is the primary, the highest stress. Right? So as I mentioned a bit earlier, also horizontal stress cannot be evaluated directly. You need to do a Likov test and understand that the trends. So what's the Likov test actually is you drill a fresh formation after setting a casing. This could be 3 to 4 meters. Then start pressurizing that the wellbore from the top with casing plus that drill, the freshly drilled formation. Then first you reach that we call FIT. It's the first gradually. This is we call formation integrity test. So if you're not sure that your formation is gonna behave and then gives you a good rate, you can also stop here with the FIT. But if you want to continue to understand the leak of area, then this starts to deviate. Of course, you are plotting this pressure versus volume, not pressure versus time, to get everything right. Of course, to normalize with the other effects. Today also we can measure the pressure downhole and surface with the cement unit. And of course, if you continue, this will deviate, and then you're going to reach that the frag propagation point. Then in this area, you frag the formation. Then eventually pressure will drop to fracture propagation pressure. We call FPP here. Then if you continue pumping, you're going to reach that fracture closure, and with the ISIP, which is the instantaneous shut-in pressure, then fracture propagation will start again. So basically, normally we do this with the mini frag operation. But for the casing, that we normally leave it at the leak off trend. Once you see the leak off, then you stop that. You know that your leak off trend. So with the petrophysical response, we have again I mentioned we have resistivity. Again, it will give an anomaly if you're gonna pass through an overpressure trend. will change direction. And of course, normally what we have here is the with the seismic input as the vertical velocity profile, which is given in meter per second. You can also convert this to 1 over velocity. It gives you the delta t. You can use it easily microsecond over feet. So this is basically when you do logs, we get this log with the acoustic tools, and you have also the trend same time. Then of course, if you're having the density measurements, similarly, the density also creates that anomaly with the overpressure trend. So let's look at an example. This is a well A. We have the it's a wildcat. There's offsets maybe distant of maybe 60 to 70 kilometers in offshore. We have just given that velocity profiles could be high and low. There are two curves, but just look at this. With the high curve, we just divided to A, B, C, and D, and this is the expected lithology column. So here A is we have velocity increase with depth, which is normal pressure expected. So B is velocity constant with depth, perfect seal, right? So this gives you a perfect seal condition, increasing at the same rate. So we expect the pore pressure will increase here on the B, same rate as the overburden. Since we are only on the clay, we are not exposing with the sands. But after B, on the C area, we have the sand layers. Then velocity increasing with depth, but no pressure increase. Again, trend change, it's uniformly changed with the expected overburden trend. Then on the D, of course, you see a velocity reversal. So any velocity reversal you're gonna see from the seismic, it gives you a hint that you might be indicating that secondary mechanism with the pore pressure, which might be indicating of some pore pressure increase, right, relatively. So moving on, of course, with some engineering judgment, you do this and create that pore pressure model. Again, first you do the your overburden gradient, which is here is the purple, is the pink color, sorry, and the blue is the frag gradient, which comes from the Miller's approach. Then you have two curves here, minimum and maximum pore pressure curve you can obtain. And then you define your basically the mud weight window. Then of course one of the other critical input is the temperature. You need to take into consideration the temperature also has an impact on if you have some clay type like cementite and illite diagenesis, especially you expect this on the C region. Then so some of the density and sonic acoustic logs will also give you an idea while drilling those formation. So you include this also into the modeling, and you create your pore pressure window. So as you can see here, it's rather narrow drilling window, typical geopressured offshore well. And of course, so there's one section here. You have maybe a go with the one casing, but several areas here. It's question mark that you can cross with the maybe 1, 2, 3, 4, 5, 6 casing string, or maybe you can use managed pressure drilling, which is maybe another subject to talk, in upcoming meetings. So here, rather a complicated well to drill, especially after this interval. Then below this, you have the 2 casing intervals. You can complete this well. And again, here is the minimum stress has been calculated based on that, correlations, since there's no logs available to calculate the Young modulus and Poisson ratio. But there are cases like, you might have that, same data set and gives you 3 different outputs. Like here, this can easily give you an easy well to drill, to design the casing, or challenging, or totally undrillable, based on that assumptions you are using as a Eaton exponent, right? So that's why regional understanding and offset well is critical. Here, what you do, of course, if you have such a well, which means that normal standard logs doesn't gonna help you. So then maybe you can utilize formation pressure bar drilling while commencing this operation. Then you can identify your pore pressure trends, right? I'll come and explain this FPWD in a bit also. Just to last slide, then again, once you do that, especially pore pressure prediction, you are basically calibrating that model I would say that you are torturing some of the data, then of course some of the things that you calibrations, it might really mislead you. That's why, especially for offshore drilling, uh, when you do the models, of course you have the critical inputs from the third parties. That's why you work with several other parts that you define probable and good case that you can model that casing design for deep water well, for instance. So now let's look at a bit of a wellbore stability after the pro pressure models. So as I mentioned earlier, we have the, first we need to do formation tops and unconformities and faults with the with of structural analysis. Then this will go to the mechanical stratigraphy. We do the rock fabric mechanical supports and model selection. So then we come to that, as mentioned earlier, Young modulus Poisson ratio, friction angle, UCS, and stress calibration and stress direction, which completes that rock mechanical models. Of course, with the 1D 1D Earth model, vertical stress is critical, and then of course you need to reach that minimum maximum horizontal stress and pore pressure, rock strength, friction angle again. Those are the key parameters. You drive this versus the true vertical depth. When you do 2D mechanical models, you can include maybe a bit of a faults and structural dips as well. You can include, but the stress still not really equilibrated. You can have some allow that stress gradient change laterally. You can try to see that impact on this on the 2D mechanical earth models. But of course, your ultimate goal is to reach that 3D mechanical earth models. First, you start with surfaces. Then, of course, you have to fill the surfaces between that with the volume. Then, of course, you have to model that rock fabric in that volume. You need maybe some rock tests, or some additional logs, of course, to once you add that model. Then, of course, you have to do the meshing with that model, and then try to reach that finite element mainly is an approach, the 3D mechanical earth model. So again, this case we are fully equilibrated with the stress state, right? So today, there are several, third-party softwares like the Petrel Visage and Javel, Gopher, Elfen, Flux 3D. They are in the oil industry. There they can utilize these approaches, right? Try to do once they do the 3D models. And of course, you don't really stop with the 3D. Once you change the, maybe you do production, especially in the North Sea. I was working there. That 4D seismic really critical. Try to see that spatial and dynamic variation change with over time due to production. That's also really becomes one of the key inputs that that 4D seismic. So eventually, for the future, on offshore in Turkey, definitely the 4D becomes also critical tool for us. Again, the core data, it's really must have, right? So in generally, in everywhere, companies, operators, they are lack of core information, because the petrophysical logs not always enough that to characterize the rocks. So you need to really do some calibration. And really also identify certain features that you cannot identify with the log averaging, which is sometimes acoustic log average the 3 feet of 1.5 meter, but there are some features maybe is there less than maybe sometimes 10 centimeter. So only cores will tell you the direct information, right? So those could be triaxial test, uniaxial test, of course, tensile strength, Brazilian. There are several ways, several methods you do rock testing. And on the core again, cores mentioned earlier, coring is really logs is really critical to get the mechanical properties and then to produce them on a continuous format. And of course, you have the sonic logs, the images, and again the wireline formation testers, right? So just to say that we have on the left side, so that commonly we are what's using offshore Turkey that as a formation tester. which we called Saturn, or the 3D probe. There are 4 probes, with about 19 centimeter each. Then of course this can be done also in LWD. It's been used also in the past in Turkey as well. It's been used heavily also in the North Sea and other offshore environment. You have also the probe type tool, not like a single pecker type. You can also measure pressure, and lately also you can take samples, which was the technology that I was worked back in my previous career. On the pressure wire drilling tool, of course, there is a probe. Of course you are circulating the same time, and then of course you have to stop. And the gauges is available. It's similar to what we have gauges on the wireline formation testers, like what we use today is the MDT. The data, of course, when you get that real-time data, we are using multi-pulse telemetry. I'm not sure you are really know that the fundamentals. You are using a MWD tool, a part of that BHA, and that pulses that in the unused pulses that MUD and produce the binary system 1010. It's maybe on itself maybe is another discussion and maybe a speech topic. Maybe we can do this later on. So of course you get certain data frames, but once you brought the tool to surface, you get the memory. So here that memory data versus the real-time data. The good thing is that they are on top of each other, because there is a certain algorithm running in the tool that it gives you that the final reach pressure buildups. So you hear that you see the pressure has been repeated several times to make sure that we are measuring the correct pressure. So here that we have the hydrostatic. This is our the overbalance, right? From here, this is the mud pressure. Here is in bar scale. This comes from the North Sea, about 305 bar, and formation about 220 bar. So here is 80 bar. There's overbalance, but then this is the drawdown, right? So and this will give you an idea about your mobility or drawdown mobility, if you are familiar. And of course, in the past they were trialed that to produce LWD dual pecker, especially to target that thinly bedded zones. Again, there has been some trial tools has been created. It's been used. This was Legacy Pathfinder. I was involved a little bit, when back in North Sea. But after that, there's some complication, of course, because this rubber you cannot set 10, 20 times, maybe limited times. But of course, this was the tool that while setting, you are circulating line, then you can measure almost like a 1 meter interval. You can measure the pressure, or you can take sample. Of course, this is again while drilling, with the drilling BHA. Moving on, then of course, then it comes to that real-time drilling and well information. It's really important. So I have, I guess, 10 minutes, so I'm concluding soon. Then try to understand that mud weight window, as I mentioned earlier. We used to do like this is in Saudi, create the drilling quality indicator that you give a heads up to the drillers that where you're going to expect some potential mud weight increase, where you're going to expect some potential peckoffs and some cavings, right? So this is what we used to create for the horizontal wells. Then of course, to able to cross that fractured zone, this is also we are now applying also in Turkey in horizontal wells. You need to cross as many fractures as you can. Then of course you have to drill towards the minimum stress. Then while drilling with the LWD tools, you can measure the images, and you can measure the fracture network, and you can create that rose plot. It will give you that maximum stress direction. Here in this case, like 330, 320 is the north direction, towards north. That this is the maximum stress direction in Adıyaman area. Again, just show you maybe one brief of examples that this is one drilled horizontal well and images acquired while drilling in Adıyaman area. Again, you see that there are some breakouts here because we are drilling towards the minimum stress. These are the fracture fracture corridors, fracture mapping is mapped. You see that every meter you have 4 or 5 fracture crossing the horizontal wellbore. Right? So again, as I mentioned earlier, you can create that plot. One thing, of course, you drilling towards the minimum stress, you create a breakout above and below the formation. Right? To able to cut all this fracture network. So having this type of wellbore, of course, creates a problem with the wellbore stability. But you need to sacrifice sometimes the wellbore conditions to able to get maximum fracture has been cut through, right? But if you do same drills towards the maximum stress direction, you create the washouts on side by side of the horizontal well. Just a brief summary that what concludes that just I'm summarizing it. The mechanical model. You have the fluid information, mechanical properties like Young modulus, Poisson ratio, friction angle, UCS, and the stress, rock stress. Right, those are comes from the leak-off tests, and again. Pressure can obtain from the MDT, RFT, and mod logging also give you an idea about if you have some increasing gas trend. It gives you about the pore pressure also. Those are the ways it creates it completes the circle. Just to give you maybe the reference that you have the log measure the TCO and the compression and shear and bulk density. This is how you calculate the Young modulus and Poisson ratio. Again, these are needs to be calibrated because these are all dynamic measurements. Because the logs we are requiring it's high frequency but with small strain amplitudes, right? But with the deformation on the static condition happens on a low frequency, but a long time scale with high strain amplitudes, right? So that's why every dynamic elastic properties needs to calibrate it with the core data, convert into the static information. If you don't have core, you have to use some correlations, right? It's given by the software. Similarly, the uniaxial compressive strength is really there's a correlation. If you don't have the core data, you can use that Young modulus static correlations, which is available to calculate that UCS values. And friction angle similarly, of course, is the best way to get from the core measurements. If you don't have, there are again some correlations given based on gamma ray logs and spectral gamma ray logs as well. With the shale and sand, there are certain numbers, and you can estimate the internal friction angle from lithology. And moving on, of course, as I mentioned, stress direction is critical, either from acoustic logs or image logs. You identify where is the preference for the stress direction change. So this case, you see that it's about 300 degree, right? Is the maximum stress direction. So then again, what are the commonly observed deformation mechanism? Shear, the tensile failure, natural fractures, right? And laminated drugs, bedding parallel wellbore, and fault activation and spalling, right? So those are the things that drillers and the while drilling, you don't want to see this type of features. Of course, it sometimes happens, and then you get losses or you get stuck, you get problems. While drilling, of course, the receiving the cuttings to surface and rig side, a part of the collaboration is critical. What type of cuttings you are receiving is blocky or angular. It gives you an idea that what type of environment you are in. You are near balance or under balance conditions. You can also get an idea about from the cuttings. Like if receiving splintery cavings, which means that you are having tensile failure, you are really getting the breakouts, and then you are really exceed that the mud weight is below the pore pressure, which means that you need to increase the mud weight in this case, right? Angular cavings, if you have shear failure, you are starting seeing this with the breakouts. Then you need to do some change and maintain that, hole cleaning and other things that on the on while drilling, right? And of course, if you are receiving a mix of these things, that then you are maybe really in unpredictable, zones you are going through, which means you really keep eye on everything, all the drilling parameters, and maintain the mud weight. Also, there are due to time change, due to time exposure, especially if you are dealing with both water-based mud and shale sand sequence, with the poor inhibition, you get loading this near wellbore and then creates some swelling, and swelling creates the problem, right? Of course, if you have some reactive clay, it also is critical. You need to understand this, and some mechanical wear as well. It creates a drilling problem, especially you are creating some one side and additional dogleg severity. If you are touching one side that the bottom wall assembly, also you are creating some mechanical wear as well. Today with the downhole shock measurements, you can really understand this. If you have that measurements coupled with that with your BHA, you can understand these behaviors, right? And the reactive clays and poor inhibition, then of course there are some stabilizers that maybe you can change the mud type. You go to the OBM rather than water-based mud. Stable window. Again, we have a starting from the pore pressure to the frag, we have the green stable window. But then, of course, sometimes we have to live with that safe window, and we have this blue area here. But of course, we would like to stay in that green area to maintain that the mud weight and ECD, of course, ECD, which is the equilibrium circuit density, which is what you are facing the wellbore environment, right? And you have to stay in the green zone. As I mentioned earlier, there are things that we can control, things that we cannot control, but there are several other factors that it brings that drilling geomechanics as a team approach, and the collaboration really a must with several parties. Just show you one example on the wellbore study prediction. Let's say we are going through, we have several offset wells like C1 to C3, D1, and then we are planning to drill a well in this location, which is the green is KA1, and then we are crossing two faults, really isolate this the features, and of course here we have a planned well, we are the formation names, and we have the offset wells. Again, we've been cross this, and we have some leak-off tests and some RFD data from the offset wells has been there to use once you plan for a new well gonna drill, which is the KA1. So basically, you need to work on this each wellbore offset well one by one, right? So you have, let's say, you have the logs. Basically, you have this is the sonic log and the gamma ray log and the casing design for offset wells. And then this formation is, of course, due to the faulting area, the formation tops are changing. Once you look at the 2D, the seismic is poor here because of geological environment, and the log quality sometimes question mark, because sometimes there is no logs. Like this case, because of drilling issues, like this one, there is no logs here to able to use. But at least there are a couple of wells. You have a complete set of logs to be able to use model predict the new well is going to drill in K1. So you go through drill. That time depth curve, which is that most critical, actually the input for us. We call the all the history of that well during drilling, what has happened in each formation. This needs to be drive for each well and digest it with the team and discuss what are the problem happen while drilling. Then, of course, you create a 1D mechanical model using that methodology as I described earlier. Create the model across the zones we drilled and logged. Of course, key input here then again the predictions, and this is the caliper measurements. So prediction needs to really honor that the caliper failures happen, like in Gerdush here in this case. Then based on this, you create a prediction model using each offset and estimate what is the safe envelope, what is the safe mud weight envelope while you're drilling to Shelmo, Hoya, Gerdush, Becirman, Altgerma, and other formations, right? So this is basically it becomes like a roadmap. When you plan this, when you plan the mud weight, when you plan, of course, the casing strings. So then, of course, you create this plot. They say you make a certain design, then your design based on offset 1 or offset C1, you reach certain numbers, and based on C2. So basically, for each offset well, if you have that similar type of environment, what will be your best mud weight, and what is your leak of trend? Basically, where you're gonna see that mud is gonna be losing into the wellbore. So this is actually again, everything here is in PCF. You have to divide by 7.48 to get PPG, and divide that 8.64 to get the gram CC if you want to convert in SI units. Right? But anyway, for the onshore operation, we are using the PCF, pound per cubic foot, basically. So final words, again, the seismic, that's one of the critical inputs if it's really good, but if it's really bad, it's really also gives you give you maybe some results that is not really reflecting the reality. That's really seismic needs to be really good, then you're able to use for the pore pressure and for the, of course, the also for wellbore stability. Then eventually logs needs to be calibrated, and you have to reach that 1D model for each wellbore, and those are needs to be populated, right, with the 3D space. And of course, once you're acquiring more wellbore in the region, you keep updating your pore pressure model, 3D cube, and of course, then you have to initialize stress model, calibrate all the stresses, right? And of course, this starts from the T1, T0, which is the before production, and after production, of course, you need to forecast that potential change in the environment or fault movements, fault instabilities, compaction subsidence, right? Once you have this calibration, but the iteration doesn't stop, then of course maybe you need to acquire another 4D seismic and you start from beginning again, keep doing the cycle. So again, every step you involve with the several stakeholders like reservoir team, petrophysics team, drilling team. That's why I mentioned earlier that the geomechanics becomes the interface of all this, because eventually produce the output for use by the completion engineers and reservoir engineers, right, and drilling engineers as well. Final words, just to mention, never let computer speaks for you. So I know people likes to use that software, but software is a software. Yeah, I mean, it really comes that your offset understanding, regional understanding. There are things that we cannot really calculate. There are things that you cannot directly model, and you need to really do a bit of an art approach to make sure that you create a good work, right? And remember, I mean, basically, the final word is 2:26:22. Still the Bolt pilot, Gazi Koşusu record, 1996 from the horse race. And again, what's your shoe to shoe? What's your KPI, right? So always you need to think about this, either shoe to shoe or measurement to measurement. What's your KPI? Thank you very much.
Thank you so much, Mr. Adil, for the informative and insightful presentation. And thank you so much for giving us your valuable time and accepting our invitation for today. Yes. So, without any further ado, we actually have a couple of questions for you, Mr. Adil.
Yeah, sorry for my camera didn't work today. That's why you
No,
don't see
it's
me,
so
but
okay. No,
I'm here.
it's
Yeah,
so okay. It's so fine.
yeah,
So, if I may forward the first question.
yeah.
So, do you have any experience about machine learning application in geomechanical models?
Who's asked the question? You don't
Do
know
you
the.
have
No, no.
experience
Who
about
asked the
machine
question?
learning?
Yeah, who asked the
Yes.
question? Is the you don't refer the who asked this question?
So, it's actually a question from me.
Ah, from you. Okay, sorry. Okay,
Yeah.
no, very good
So,
question.
do you
Come
have
on.
any experience
Yeah.
about machine learning application in your geomechanical models?
Um, Good question because there are tons of time data sets available. Okay, we are mainly acquiring quite a bit of things against the depth, but then while drilling, there are lots of time data sets is sitting there and no one is touching.
Yeah.
Uh, okay, I mean, I see on the last few years myself. Okay, uh, I know machine learning definitely can be utilized on this, but I didn't really use myself. But I see lately, especially in Norway, there are companies try to utilize that time data sets, uh, try to estimate like maintenance, for instance, maintenance period for drill bits or the pull out of sequence for bottom hole assemblies, right? Based on the predictive models, predictive machine learning. So that's the open area for future. Uh, we are old, but we are still learning. But again, you need young brains, young people to dive into this the machine learning area. Definitely a good subject to work.
Thank you so much. So, my second question is, what would you say about geomechanical problems in the Black Sea? Do you think that the sand production will impose any problem there?
Um, Again, another good question. Actually, I skipped that. There is I show you a slide that from Norway
Yeah.
and real field. Uh, Actually, this is again from mpd.no. I really suggest that people go to mpd.no. Those reservoir and the field information is public. You can download. Uh,
Yeah.
I think the slide number, forget now, but then, okay, this field actually very shallow. It's only reservoir temperature is like 11 degrees C. Okay,
Yeah.
if I go back I just want to go back maybe to, can I, just 1 minute.
But the site is not showing if you're trying to.
I'll bring it
Yeah.
down. Just I'm trying to bring
Okay.
it down. Yeah, sorry.
No, it's okay. It's okay.
So basically, if you take the precautions, take the measurements, take the plans right, you can of course you can model. You can easily, yeah, this one. Okay. See, this one, it's okay, about 400 meters water depth. Still, you have to do, this is not for a jackup. This is maybe for semi-sub. The gas field, it starts only 160 meters from the seabed, okay?
Yeah.
And these wells, if you go to the mpd.no, this Payon field, it's produced 1.2 million cubic meters a day, okay? This is
Yeah.
sandstone, by the way. Sandstone, of course, there is a gas water contact. So this is really, I would say, is very loose sands, very loose. I mean, like the sands that you have maybe in the beach, maybe that looser than that, right? So
Yeah.
this is managed with the gravel pack, of course, with a certain type of gravel pack, and of course we are doing the same approach in Black Sea. That, yeah, of course, we can measure, we can mitigate the sand productions if you take the measures right in the first place.
Yeah. Thank you so much, Mr. Adil. It was quite actually a very informative and insightful presentation, to be honest. And I thank you again for accepting our invitation. So, no more question came to our chat side. So, I think this is for today. And we thank you so much again. And we hope to see you soon in our upcoming seminars.
Okay, thank you so much.
We thank
Have a
you
good day.
so much.
Yeah.
Have a good day too, Mr. Adil.